Today we're going to be learning about linear approximation and differentials. This is section 3.10. So linear approximation, as the name implies, is using a line to approximate something. And the reason we do this, lines are easy to plug numbers into. So suppose I had some kind of a nicer, or maybe not nice, a curve going on over here. Then what we've been doing so far is we found tangent lines of things. But if you notice that as long as you're close to where you created your tangent line is very close to your function. And because of this observation, what we're going to be doing is we're going to try to use the tangent line to estimate values of the function. And there are good reasons to do this a lot of times. Take, for example, something we don't know how to calculate, natural log function. Looks a little bit something like this. I am 0 and x is equal to 1, and then x is equal to e, I'm equal to 1. Y is equal to 1. So, if f of x is equal to the natural log of x, I know some easy to calculate things. I know that f of 1 is equal to 0, and f of e is equal to the natural log of e, which is 1. But a number that comes up rather frequently, especially in some of those radioactive decay problems a couple days ago, is the natural log of 2. So I want to calculate what is the natural log of 2. And what I'm going to do is I'm going to try to use a tangent line to estimate this. But it helps to make your tangent line as close as possible to the number you want to estimate. I don't want to use 1. 1 is really easy to calculate, but e is closer to 2 than 1 is, since I know that e is approximately 2.71882818280459. So what I'll do is I'll find the tangent line to f of x equal natural log of x when x is equal to e. So in order to do that, I need the y value associated with e, but I've already done that in my picture. So I need the point e comma 1, and I need a slope. I need f prime of x, but the derivative of natural log is 1 over x, and in particular I need f prime of e, because that's where I want to make my tangent line. So I have a point and I have a slope. So I can make a tangent line. I can have y minus 1 equals the slope 1 over e times x minus the x value e. And if I rewrite this into slope-intercept form, I have y equals x divided by e minus 1 plus 1. So those cancel. I'm just left with y equals x divided by e. And since I'm using my tangent line to estimate my function, I'm going to plug 2 into my tangent line instead. And I'm going to get that natural log of 2 is approximately equal to 2 divided by e, which is not terribly helpful for some of us who don't have a calculator. But it turns out that this is in turn approximately equal to 0.735759 compared to the natural log of 2, which is 0.693147. That's pretty close. What I'd like to do is get kind of a bottom line formula for doing linear approximation so I don't have to try so hard. So let's start with a function. We'll have a function f of x. It should be differentiable because we need a tangent line. And we need an easy to calculate number. And I call this my easy A. Now you can tell people you have an easy A in calculus. So for the tangent line, at a comma f of a, I'm going to have y minus f of a equals the slope f prime of a times x minus a. or I'll have f of a plus f prime of a times x minus a. And this here, this tangent line, this is my linear approximation, which is sometimes called the linearization of f of x at a. And it's a very nice looking bottom line formula. In fact, I'm going to try to use it right now. Can't wait. But the number I want to approximate is the square root of 2. And it's tempting here to just use the square root of x as my function. Whatever number is bothering me in here, the number we provide, this is always going to be the x, which we need to estimate. And I need to choose an a, which is easy to calculate for the square root function. The problem with this is the only things which are easy to estimate for the square root, or easy to evaluate for the square root, are x equals 1 and x equals 4, and both of those are kind of far away from 2. But I'm going to go ahead and try it. I have that f of x will be approximately equal to L of x, which is equal to f of a plus f prime of a times x minus a. Now just for fun, I'm going to go ahead and try both of these. I'll try a equals 1, and I'll try a equals 4. So doing 1 first, I'll have that the square root of 2 is approximately equal to L of 2, which is equal to f of 1 plus f prime of 1 times x minus 1. Since f of x is equal to the square root of x, f prime of x will be equal to 1 over 2 times the square root of x. So down here, f of 1 is 1, plus 1 over 2 times 1, multiplied by x minus 1. X is 2. 2 minus 1. So I ended up with 1 plus 1 half, or 1.5, which is okay. Maybe the other one will be better. I'll have the square root of 2, which is approximately equal to L of 2, which will be f of 4 this time, plus f prime of 4 times 2 minus 4. And what do I get out of that? Well, the square root of 4 is 2, plus 1 over 2 times the square root of 4 is 1 over 4, times 2 minus 4, which is negative 2, which is equal to 2 minus 2 over 4 is 1 half, and I get the same value. I get 1.5 again. So my question is, can I do any better to estimate the square root of 2? And the answer is actually yes. If we recall, the square root of 8 is actually equal to 2 times the square root of 2. Because 8 is 2 times 2 times 2, and so 2 of those 2's pair off to come outside of the square root. So I'm going to use linear approximation to estimate the square root of 8. Here I'm going to be using x equal to 8, and I'm going to use f of x equal to the square root of x. And this is the function I want to approximate with a line. Close to 8, we have 9, and the square root of 9 is equal to 3. So I'll use a equal to 9, since the square root of 9 is easy to calculate. It's equal to 3. Then what do? I just chomp out my linear approximation formula. My linearization is equal to f of a plus f prime of a times x minus a. My a is 9 and my x will be 8. All I need is f prime of x. So f prime of x is equal to 1 over the 2 times the square root of x. So f prime of 9 will be 1 over 6. So L of 8 will be equal to f of 9. Let's go ahead and use the square root of 9 plus f prime of 9, which we found is 1 over 6, times 8 minus 9. And what do I get out of that? I get 3 plus negative 1 over 6, which is equal to 18 over 6 minus 1/6, which is equal to 17 over 6. So I found that 2 times the square root of 2, which is equal to the square root of 8, is approximately equal to 17 over 6, which is a nice small number, rational number, whatever that means. Which also means that the square root of 2 is now approximately equal to 17 divided by 12. Now how much better is this than the 1.5 I was getting earlier? Well, the square root of 2 is approximately 1.414. And 17 over 12 is actually 1.416, with repeating sixes. It is actually significantly closer than the 1.5 I got from the other versions of this problem. Moving on, I'll unveil the great secret of linear approximation. We had that the function was approximately equal to f of a plus f prime of a times x minus a, or f of x minus f of a is approximately equal to f prime of a times x minus a, or f of x minus f of a divided by x minus a is approximately equal to f prime of a. And this is exactly one of the things we use for the derivative. Remember that the limit as x goes to a of f of x minus f of a divided by x minus a is equal to f prime of a. So as long as my x values are close enough to a, this value on the left is a very good estimation of the derivative, which is why the linear approximations work. As long as I'm very close to my a, my tangent line, which I end up with up there, is very close to my function. But this also gives us a different method of approximation, because this f of x minus a, this is a change in y values, and the x minus a is a change in x values. And so one of the ways I've written this before is this is a change in y over a change in x, versus the f prime of a is equal to a dy over dx at x equal to a. The difference between the left-hand side and the right-hand side, or the difference between using triangles and lowercase d's, is whether or not a limit has been applied. Technically, this dx is after the limit has been applied, and so the dx is equal to 0 and the dy is equal to 0. But this is a 0 divided by 0 indeterminate form, which is why we can say it actually has some interesting value, because we did a limit to evaluate what that could have been. So rewriting this from what I had before, I have delta y over delta x is approximately equal to f prime of a, or in particular, delta y is approximately equal to f prime of a times delta x, which also makes sense in some other words. If I increase my x values a little bit and I have a particular slope, then that's going to give me an estimation of the increase in the y values, because the slope is exactly rise over run. I'm applying a slope for a short duration in my delta x's. So these are called differentials. Books will often go ahead and use these, and they'll write like dy equals f prime of x dx. But like I said before, dy and the dx are equal to 0, and f prime of x is equal to dy over dx. So you're not really saying anything here. You're just saying that dy is equal to dy over dx times dx, which dy equals dy. Fabulous. Amazing. Good job. Appropriately, you should always be using the triangle version. Triangle y, the change in y is approximately equal to the derivative multiplied by the change in x. Because the versions with these, those are equal to 0. We shouldn't really be using those. But the triangle versions, those are actually discrete distances that we can measure. So how do we use differentials? Well, let's try an example. So we'll suppose we have a spherical jawbreaker that has a radius of 1.5 centimeters. And after some time sampling the jawbreaker, the radius measures 1/2 of a millimeter less. That is, the radius now measures 1.45 centimeters. We want to estimate the change in the volume and the surface area. So what happened was our radius, our old radius, was 1.5, and our new radius is 1.45. And for these problems, you should always be dealing with new minus old. I get minus 0.05. That right there, that is my delta R. That is the change in my radius. It's negative because my radius is shrinking. It got smaller, so I have a negative change. And my differentials, this is going to be delta. First I'm going to do the volume, so delta V would be equal to the derivative of the volume multiplied by the delta R. And my surface area, my delta A, would be equal to the derivative of the area multiplied by delta R. So let's find out what these are. The volume of a sphere is 4/3 pi r cubed. So V prime is equal to 4 pi r squared. The area is equal to 4 pi r squared, which is a nice coincidence with spheres, and its derivative is 8 pi r. Now what I always want to do is plug in the original values. So what I mean is my delta V will be equal to V prime of 1.5, my old value before I changed, multiplied by my delta R, which is 4 pi 1.5 squared multiplied by negative 0.05. And what do I get out of this? I have 4 pi, that multiplies to 2.25, and I'm going to change this to a fraction because I don't like decimals and I really like fractions. This is 5/100. This is minus 5 over 100. So 4 times 2.25 is going to be 8 plus 1, which is 9. So I'll have 9 pi times negative 5 over 100, which is 1 over 20. So I end up with negative 9 pi divided by 20. I got a negative number for my change in my volume, which makes sense because my jawbreaker is shrinking. And these have units. The change in my volume is negative 9 pi over 20 cubic centimeters. Similarly, for my area, surface area, delta A would be equal to A prime of 1.5 multiplied by my delta R, which is 8 pi times 1.5 times delta R, which is minus 0.05. And out of that, I get 12 pi times negative 1 over 20, or, there we go, negative 3 pi over 5. And this also has units. It'll be square centimeters. It's also a negative value because the surface area is also shrinking as the jawbreaker shrinks in size. These can be used to estimate maximum possible error. The book makes a pretty grave error. It says that this will give you the maximum possible error, but that's totally untrue. Because there are frequently examples, it's very easy to make a problem where the maximum error is actually greater than the number you get from the differential estimate. And the way the error problems work, I'll just scroll back up to my jawbreaker. If I have an error in measurement, say for the radius, then that's going to correspond exactly to an error in the volume. So let's treat these changes in volume and area as an error problem. Delta V would be an absolute error. Again, this is an estimate. It does not give you the actual maximum error. Delta V divided by the volume is relative error, or relative change in size, which your error could be very, very large, but it might be very small based on the scale of your problem. Or the other way, if your problem is very small. So in this case, my delta V divided by V is equal to negative 9 pi over 20 all over 4/3 pi 1.5 cubed. I can cancel these pi's, but I think I'm out of luck simplifying this otherwise. I'll have minus 9 over 20 multiplied by 3 over 4 times 1 over 1.5 cubed, which is negative 27 over 80 times 1.5 cubed. Eyeballing this is a much smaller number than I had before. And then there is percentile error, delta V over V, multiplied by 100. Which is basically just a different way to say the relative error is you have made a percent increase or decrease from your original. So let's talk about the settings of error in a real problem. So let's suppose we are cutting a disc to have a radius of 4 centimeters. And I want to estimate the error in calculating the area of the disc, assuming that the error in measurement is at most 1 millimeter. And here 1 millimeter, that's equal to 0.1 centimeters. So this is a differentials problem. We're going to have delta A, the change or the error in the area, is approximately equal to the derivative of the area multiplied by the change or the error in the radius. So I have here delta A is approximately equal to the area of a circle is pi r squared. So I have 2 pi r times delta r. And what I use for these error problems is I use the assumed or the target value to plug in. So I have delta A is approximately equal to 2 pi times 4 multiplied by a plus or a minus 0.1 centimeter. And the reason I have a plus or a minus is because I gave a number for the absolute error in my measurement, which could be above or below my intended target, which means the error in my area is approximated by 8 pi divided by 10, plus or minus, and those units are square centimeters. Let me reread the question. It just says estimate the error, so I'm technically done. But the book might ask you to estimate the relative error, and the relative error is just the delta A divided by A, which would be plus or minus 8 pi over 10 divided by pi r squared, which is plus or minus 8 pi over 10 all over 16 pi, cancel, cancel, giving me plus or minus 1 over 20. So if I'm talking about this in percentile error, I have a plus or minus 5% error in estimating or in calculating the area of my circle. This is the last topic we have for exam 1, Exam 1 will cover everything from Chapter 2 up until this section. Be sure to do the web assigns, and be sure to let me know if you have any other questions. And make sure that your proctors are ready to receive you.